Welcome to my lecture series on course, that is fluid mechanics. Fluid mechanics will be composed of fluid mechanics 1 and fluid mechanics 2. The level of this course is undergraduate programs of engineering and technology students. Basically, fluid mechanics 1 will be composed of the fluid statics, fluid kinematics and fluid dynamics, and the fluid mechanics 2 which will be composed of open channel flow and the fluid machines. Now I am going to start with new lecture series uh, on fluid mechanics 1. In fluid mechanics 1 we will study the fluid statics, which is composed of 4 chapters, that is properties of the fluids, then measurement of pressure, hydrostatic pressure, buoyancy and flotation. In fluid kinematics we will study the fluid kinematics, which is composed of the properties of velocity, acceleration, discharge, radial acceleration, and this vorticity, stream function, potential function and their relationship. And in fluid dynamics we'll study the energy equations and their applications, mouthpiece, orifice, notches, spheres, and closed conduit flow or the flow through pipes and boundary layer theory. These aspects we'll study in fluid mechanics 1. Some part of the dimension analysis and the model analysis will be also considered in fluid mechanics 1, and some part will be considered in fluid mechanics 2. So let us begin with the today's, that is our lecture series on fluid mechanics 1. I welcome to my channel. Please subscribe, please share and please like this channel. Thank you. Now let us begin with our first lecture, that is the properties of the fluids. Thank you. Let us begin with our subject, fluid mechanics 1, lecture 1, fluid properties. In this topic we will study introduction, mass density, specific weight, specific volume, real fluids and ideal fluids, and viscosity. The subject fluid mechanics deals with the study of the motion and general behavior of the fluid governed by the law of conservation of mass, laws of mechanics and of thermodynamics. The laws of mechanics refer to the Newton's second law of motion. Basically, the fluid mechanics is totally based on the 3 equations, namely the continuity equation, energy equation and the momentum principle. And all the equations, they are the form of one or other equation. So basically these are the 3 equations that we are going to study one by one in the due course of time. Now whole fluid mechanics is composed of the 3 contents, that is fluid statics, fluid kinematics and fluid dynamics. So in fluid statics, what are the properties? The study of mechanics is basically composed of fluid statics, when the fluid is at rest. A study of fluid when it is at the rest. Then hydrostatic, it is a part of study of incompressible fluid at the rest. Then aerostatics is a study of compressible gases. Then the next, it is fluid kinematics, that is the free motion of fluid particles without any external force. Whatever the motion takes place, it is known as the fluid kinematics. For example, velocity, acceleration, then vorticity, then radial acceleration, radial velocity, all these vortex flow, all these will study in the fluid kinematics. Then it is a study of flow pattern in relation between the velocity, acceleration, discharge, speed or any kinematics behavior of the fluid without reference to cause of motion or the force or energy. So anything without cause of any force, it is a free motion of fluid particles or the fluid is considered in fluid kinematics. Then it is fluid dynamics. It is also considered as fluid kinetics because it is a force motion of the fluid particles. A study of fluid flow, that is velocity, acceleration, etc. with force or energy causing the force or energy causing the flow being considered here. So that is fluid dynamics. So whatever the dynamic action of the fluid is known as the fluid dynamics. For example, the water flow in pumps, water flow in the turbines, they are considered as fluid dynamics. Aerodynamics, that is the study of compressible or incompressible flow of gases. So whatever the compressible gases or incompressible gases in the aerodynamics, they are considered as the fluid dynamics. Then first property, very basic property under fluid property is the mass density. We have already come across since our class 10th or 8th or earlier than that. So first property of the fluid is mass density, which is known by everyone. It is the mass of the fluid per unit volume. Then the unit, it is kg per meter cube, and generally example, that is water at 4 degrees Celsius, the mass density is 1000 kg per meter cube is considered as. So it is denoted by letter symbol rho. Rho is mass of the fluid per unit volume, and in case of mercury it is 13,600 kg per meter cube, and in case of oil, let us say it is 800 kg per meter cube, because oil is lighter than the water, and whereas the mercury is heavier than the water. So the density is higher, it will sink, and if the density is lighter, that liquid will float on water. So this concept we have already came across since our standard 8. Then next property is the fluid it is specific weight. So anything by gravitational force is considered as the weight. So specific weight is defined as W is equal to weight of the fluid upon volume of the fluid. Specific weight, it is the product of mass density and acceleration due to gravity. The specific weight is expressed in terms of kilonewton per meter cube, because kilonewton is a force, or newton per meter cube. Newton is also a unit of force, or dynes per meter cube. Dynes is also a unit of force. For example, specific weight of water is 9.810 kilonewton per meter cube, or 9810 newton per meter cube, which will use very frequently in forthcoming lectures and forthcoming topics. Then next property is the specific volume. Specific volume of the fluid is defined as the volume of the fluid per unit weight of the fluid. Specific volume is reciprocal of specific weight. Specific volume is a reciprocal of specific weight. The unit of specific volume is meter cube per kilonewton, or meter cube per newton, or centimeter cube per dynes. The concept of specific volume is commonly applicable in case of gases. Then specific gravity. Specific gravity of the fluid is the ratio of mass density of the fluid to the mass density of standard fluid, that is pure water at 4 degrees Celsius is adopted as standard fluid. Specific gravity is the ratio of mass density of the fluid upon mass density of pure water, or mass density of any standard fluid. In case of liquids, the standard fluid is considered as water, or in case of gases, the standard fluid is considered as air. The specific gravity of water is considered as 1, and specific gravity of mercury is considered as 13.6. So these two figures we will use very frequently in forthcoming topics. Then next is the ideal fluids. Ideal fluid is just like an ideal student who is very punctual, who is very honest, submitting the assignment in proper time, and appearing for the examination, clearing examination in time. So just like that ideal student, it is ideal fluid. No viscosity, then no surface tension, and and mass density remains constant throughout the flow. So ideal fluids are those which are non-viscous, incompressible. Incompressible means rho is equal to constant, and have no surface tension, that is sigma is equal to 0. So they are imaginary and do not exist in the nature. Ideal fluid concept is used classical hydrodynamics to simplify the mathematical analysis of the fluid flow problems. For the simplification of the problem, normally we considered as our mu is equal to 0, that is the fluid is non-viscous, and rho is equal to constant and no surface tension. So for the simplification of the problem, we'll always use means for our undergraduate programs, we'll consider our fluids as ideal fluids. Most of the common fluids are as water and air. They are having very low value of viscosity and can be treated as ideal fluids for practical purposes without much error. Mathematically, it can be expressed as mu is equal to 0, comma, sigma is equal to 0 and rho is equal to constant. So this is the simple definition of the ideal fluids. On the contrary, the real fluids, actual and practical fluids, they exist in the nature. Real student just like that, so frequently will bunk the classes, frequently show some laziness because it is a human tendency. So similar way, so it is the real fluids. So real fluids are the practical fluids. They are exist in the nature. They do possess the viscosity. They are compressible. That is, mass density changes during the course of motion. Surface tension, they possess some surface tension in the motion. So mathematically, mu is not equal to 0, sigma is not equal to 0 and rho is not equal to constant. So this is the definition of the real fluids mathematically. Then viscosity, it is denoted by letter mu. Unless and until specified, the viscosity is always considered as dynamic viscosity. The resistance of the fluid or gas or liquid due to change the shape or movement of the neighboring portions relative to one another, because one layer slides over the other layer and they do possess some shearing action. So this is the concept of the velocity, which is reckoned by the property of viscosity. Viscosity denotes the opposition to the flow. The reciprocal, the kinematic viscosity is defined as the ratio of mu, that is dynamic viscosity, to the mass density, that is mu is equal to mu upon rho. So there are the two types of viscosities. One is dynamic viscosity, which is denoted by mu. The units of dynamic viscosity are poise, that is Newton second per meter square, then Newton second per meter square, kilonewton second per meter square, or Pascal second. And one poise is equal to 1 upon 10 Newton second per meter square. The dimensional formula for the viscosity is m L raised to minus 1 and T raised to minus 1. Next is the kinematic viscosity, which is denoted by letter nu. The kinematic viscosity is the measure of fluid's internal resistance to the flow under the gravitational force, which is given by nu is equal to mu upon rho. Kinematic viscosity is dynamic viscosity upon mass density. So kinematic viscosity nu is a measure of fluid's internal resistance to the flow under gravitational forces. That is, nu is equal to mu upon rho. The units of kinematic viscosity are meter square per second, centimeter square per second, Stokes, centistrokes, etc. And the dimensional formula for this kinematic viscosity is m square T inverse. 1 Stoke is equal to 10 raised to minus 4 meter square per second, or 1 centimeter square per second. So let us study more about the property of viscosity. The effect of temperature on the viscosity. In case of liquids, the viscosity decreases rapidly with increase in the temperature. For example, tar. If we heat that tar, it gets molten. And in case of gases, the viscosity of gases increases with the increase in the temperature. For example, steam. If we increases, then its viscosity gets increases. The flow rate, discharge, and viscosity relationship. As the viscosity decreases, the flow rate, as the viscosity increases, the flow rate decreases. For example, you can visualize from the molten tar, because molten tar is viscous and the rate of the flow is very less as compared to the rate of flow of water. The flow rate Q is inversely proportional to the mu. Viscosity and intensive property. Viscosity does not change as the amount of matter changes. Therefore, it is an intensive property. So, this is the diagrammatic representation of the effect of viscosity and the temperature. It is a measure of internal flow, as we have already discussed, that it is a measure of the internal fluid friction which is causes the internal resistance to the flow. The origin of viscosity is due to the cohesion and the molecular momentum transfer. These two factors added up to provide the resistance to the shearing action reckoned by the property of viscosity. In case of liquids, the viscosity drops with the increase in temperature, and in case of gases, viscosity increases with the temperature. Already, thank you very much for attending this lecture. Next time I'll come with more properties, that is pressure, compressibility, surface tension,